We'll start today's presentation on PFAS. So I'm joined today by Dean Adams of South Staffordshire PLC and on-site, Cara Sadler from South Staffs and Cambridge Water, and Kathy Swanson and David Hayhurst, who are going to introduce themselves. I'm not going to steal any of their thunder as we go through the presentation today. So we have been joined or come together to talk about PFAS, or per and polyfluoroalkyl substances. For those that aren't yet quite up to speed with PFAS, we're going to give a little bit of an opening as a presentation as to what they are. Some of the information I'm going to give from a sector perspective is set out in some of the other presentations in detail. So please don't worry about taking any notes or anything if I move past quickly. It just means that the other presenters are going to cover it in detail in their sections. I'd also like to just point out, if you want to ask us any questions today, we will take questions at the end. And if you could pop those into the chat and I'll moderate them. If they are really relevant to the presentation, I will bring them out at the time. If not, we've left time at the end for Q&A. For everyone else, if we could go on as silent and have cameras off, that would be helpful to help bandwidth. But as we've said, all of this will be available on the Pipeline Industries Guild website through our YouTube channel later, and it will be published on our LinkedIn pages for those that want. For all the people who are talking today, if you want to contact any of us directly, you can do so via LinkedIn. And at the end of some of the presentations, we've got direct contact details, so please feel free to use those as well in the time. So here we are talking about PFAS. What is it? So probably quite a lot of them have talked about them being forever chemicals, and you'll hear some things about how they impact the sector and what that means. But the reality is that there is no one term or one chemical that makes up PFAS. And they are really just a family of probably thousands of man-made chemicals that are in water and some in oil, but are fairly much heat resistant, water resistant, and most of them are oil resistant. We've been using these chemicals since about the 40s, and we've done that in lots of different industrial and consumer products. If you've used any non-stick cookware, fire-resistant clothing, which I know anyone that's been to site generally has these days, stain-proof fabrics, almost everyone has had them sprayed on their home sofa, firefighting foams, which do pollute our watercourses quite frequently, so they're a big focus for this. Electronics, all of these things will have had PFAS released into the environment for them. So they are here, and they call them forever because and we will touch on this later, but the carbon-fluorine bond is extremely strong. So they just do not break down naturally. And that means that they do accumulate in the soil, water, wildlife, and recently proven to be in bodies. For us, that means, as people in the environment, we are exposed every day to these things, and they do cause now, latterly, though the science is a long-term impact is unclear, they can cause disruption to your endocrine or hormonal systems. They can reduce immune system impacts. That does impact cancer sufferers. And as one of us, as 1 in 3 of us in the UK will get cancer, that's a broad sweeping statement. And they do make some diseases which are already known worse if they're in high enough quantities. We don't really know what that means in terms of every day, and legislation is now coming to catch up, which will be a theme of the presentations today. So what are the regulators doing about PFAS? The regulators weren't able to join us, but they gave us some statements today. So DEFRA have put out their 3-pillar plan. So it was released on the 3rd of February and does dictate, if you haven't seen it, go and have a look at what they are up to and where they believe that we need to be focusing on in all of the regulation for PFAS. Their 3-step plan is simply understanding where PFAS is. They don't feel that we've got a good understanding about where it is in the environment, what quantities in that place it causes us risks. So they are in a gathering phase that has started. They want to tackle PFAS pathways, so reducing PFAS usage at source, so we can remove some of those things. Firefighting foams clearly is a big focus for them, that's mentioned several times, but where we have substances where they're in very high concern, they will look at those first through the UK REACH, as you would expect them to be operating. So they want to do their tackling in terms of transition to safer alternatives, putting and developing specific thresholds which are not available today in discharge consents, and more importantly for today's conversation, strengthening the permitting requirements and the best available techniques or BAT requirements. They do not have a BAT statement in the EA yet for PFAS, but it is under development and being consulted. The third one would be to reduce ongoing exposure, removing legacy issues that they think mainly come from landfill leachate, farm spreading, sewage sludge, and industrial contamination and discharges. So lots going on, which we're going to talk on how they do that. But there is a real question which comes up quite a lot when you do the research into PFAS, which is, what are they going to do to clear it up? And we've put across our sector today supply chain, technical experts, and client side people to talk about those their views on PFAS, mainly because historically you would have expected the EA to run a polluter pays policy. In the UK, that they're not written into legislation. All approaches and legislation supports polluters to pay. What they have put out is through the EA is a statement that basically says, we struggle to identify the polluter. It's been going on for so long, we don't know what that looks like, and we don't know how those things work together. So in the interim, we're going to default to existing legislation and remove harm where possible. That means it's going to fall to the water companies and therefore their customers to currently pay. So it's important to understand what the water companies will do, because they are still responsible for the water quality and wholesome water under the Water Act at the tap, which we'll talk a little bit about water quality and those requirements. They have, however, said very clearly that the route to legislation may mean they go back to polluters, but in the interim, they want to have their three-pillar approach of understanding, reducing impacts, and legislating properly for what we currently know as today. When it comes to removal, we're going to talk a little bit about some of the removal today, what's worked well, what hasn't, but there are only 3 accepted current technologies. Not all do all things. Granular activated carbon, or GAC, GAC as it's quite often called, which it probably isn't a focus for today, but it has seen, and we'll come on to it, as being effective, but not quite where we might want it to be. Reverse osmosis, RO, everybody in the UK knows we use RO quite a bit. We use membrane technologies in lots of other parts, not necessarily full RO, but it is always costly and high intensity if you really need to do a full RO approach. Advanced oxidation, and again, those in the know, those advanced oxidation processes are AOPs, and emerging disruption technologies like electrothermal and plasma, thermal and plasma, are all in development, but have seen yet limited kind of uptake in large scale industrial applications to solve water quality problems in the UK. And where we're going to focus our chat today, which is ion exchange resin IX, and I won't take any of the glory. So in short, we know they're a problem. We know that these exist. They've been going on for years. The legislation doesn't allow for that kind of long-term polluting impacts to be picked up or swept up. So we're going to secondary primary legislation. The EA and DEFRA have put out their strong statements to say what their plan is to resolve PFAS. There have been some moves in the water regulators, both the DWI and Ofwat, to support that, but we don't yet have a legislative approach. So it will fall to the water companies, our clients and supply chains to make sure that we understand what we are doing to support that change, which leads us to our webinar today. So I hope that you find it very useful as we go through seeing those views, and we'll kick off with our first presenter, which will be Cara.
Great, thank you, Barry. I'm just going to share my screen, everybody, so bear with me while I put this in, and hopefully now you can see my screen. Fab, thank you. So good afternoon, everyone, and my name is Cara Sadler. I'm the Head of Water Quality at South Staffs and Cambridge Water, and I'm also National Chair of the Institute of Water. Being Head of Water Quality, my role covers drinking water compliance, risk management and mitigation, and a lot of regulatory engagement. So PFAS has become a very real and very practical part of my day job over the last few years. Like many companies across the UK, we've moved from monitoring and risk assessment into active mitigation, especially in those sources where we have had detections of PFAS. And therefore, my short presentation today is just going to share our experiences of using granular activated carbon, or GAC as I will as I will go through this presentation and state it, just to give you an idea of why we selected it, but actually a reflection of why we selected it, but how it's actually performed in practice and not necessarily had the performance that we was expecting originally. And it just shows a reflection on when design assumptions meet actual real water quality, and what that means for us. So just a flick through in terms of PFAS, which I won't go too much into what PFAS is because Barry's given a great introduction already. But to give you a case study from one of our sources at Sawston Mill, where that fits in with the regulatory and industry context, why we chose GAC, what the operational challenges are and cost and ESG going forward, and whether that is reasonably practical. So a lot of this Barry has shared already, but essentially the PFAS is becoming more familiar with us. Even members of the public, there is a lot of public awareness and regulatory focus, which has accelerated dramatically over the last few years. As has been mentioned, they are very persistent and they are designed to be incredibly stable, and that is why they're problematic. So they're often referred to as forever chemicals, which isn't a scientific term. It's because they don't rapidly break down in the environment. They're mobile in water and they are bioaccumulative. From a water industry perspective, that combination of being persistent and mobile is exactly what makes them challenging. PFAS has been the subject of much talk over the past few years, and we are getting better at detecting PFAS. We have improved analytical detection limits. We have more emerging toxicology evidence, as well as regulatory tightening. So for water companies, PFAS isn't just a compliance issue, it's a trust issue. And that is one of the biggest things in terms of that public awareness and knowing and hearing about forever chemicals and what's in their drinking water. Quite rightly, members of the public don't want to be drinking what they deem as forever chemicals and what that means. Just a picture there of a typical PFAS substance and some of those areas that Barry mentioned in terms of where that comes from in terms of household and industrial use as well. So this image has just been taken from the US Environmental Protection Agency. It just gives a visual on that PFAS water cycle. Again, how do we get it into our drinking water, in our raw water sources, in both ground and surface water? Now, the Drinking Water Inspectorate, the DWI, has provided a lot of guidance in terms of PFAS, and in March last year, they gave a consolidated guidance document detailing what their requirements are for PFAS monitoring, how we need to risk assess that, what our strategy is in relation to our public water supply systems. And the World Health Organization has produced, again, guidance documents. There's a lot of information out there. Essentially, there's still no limit that's been set, but water companies have a duty to ensure that water is wholesome. So although there is no statutory standards for PFAS in drinking water within England and Wales, nor is there a World Health Organization guideline value, the DWI has taken a precautionary approach and produced tiered guideline values for water companies to adhere to, and that is the 0.1 micrograms per litre or 100 nanograms per litre for the sum of 48 named PFAS compounds. So there are lots and lots of PFAS compounds that are out there, but in particular it's those 48 that our regulator is interested in understanding where we have that within the drinking water. So there's been research into the efficacy of various treatment types of PFAS removal. And again, Barry shared a great introduction into some of those. And there's just a simple table on the slide there in terms of the pros and cons of those different technology. Whilst efficacy varies by the type of PFAS, that is a big part of it, the treatment process and the source water characteristics. it does show that PFAS can be effectively removed from water sources. However, it does depend on what you're trying to remove and to what level. There is some really good technology out there, and possibly in terms of where we've spoken about the best available technology, where does that apply to? And GAC usually has up to this point sat at the top because it's known and it's simple retrofit, and it's a proven technology. However, there is some drawbacks to using GAC, which I will share in the next few slides. So to give some context into the background of the case study, so we have a water treatment works within Cambridgeshire. It treats water from a groundwater at Duxford, which is an active airfield and museum in Cambridgeshire. So the key part being their active airfield. From the few slides ago, you'll see that one of the causes of a PFAS can be from where we've had that detection PFAS in firefighting foams previously. And although we've worked with the Duxford airfield to remove that fluorine compounds within their firefighting foams, there is still that accumulation within the ground that means we have to treat it and it doesn't go away. So back in June 2021, we detected PFAS at 0.35 micrograms per litre, which was above the tier 1, above the level that we need to see in drinking water, and the site was taken out of supply. So GAC was chosen because of the rapid deployment and the cost versus certainty balance and the operational familiarity, which is a really big part of that. In terms of the site, the site was designed to treat on an empty bed contact time of 15 minutes, an average flow rate of 176 metre cube per hour, 3 GAC vessels. The idea was that we would get about 30,000 bed volumes at that flow, which would give us about 12 months of running before we had to fully replace those GACs. To note here, the groundwater quality at Sawston Mill from Duxford is very good, so we didn't have to include a backwash facility because of the challenges of backwashing that water. We were unable to discharge and run to waste in the environment because you've got PFAS in your backwash water, it's going to be going straight back into there. And following a trigger of PFAS, full GAC replacement would be required. In terms of our response criteria that we set ourselves internally, we had 3 levels that we would do before we shut the site down and carry out further investigations, and then actually carry out GAC replacement. Now, these are quite tight and stringent levels. So if you look at the original level that the DWI have, it's at 0.1 micrograms per litre. So it's a quarter of what that guidance level is. The reason being is the turnaround time of the lab samples. Generally speaking, it could be 2 weeks to 4 weeks before we got those results back. We did put Sawston Mill on a quick turnaround time, but we don't have the 24 hours to respond, and we cannot have water that, if it was above that level, going into supply for more than 2 weeks. We had to set ourselves some very conservative levels. But the performance was not as expected. One of the key things that we did as part of Sawston Mill was have a pilot plant, and that pilot plant was to operate to enable us to see breakthrough from PFAS compounds before we had it on the final water or from the GAC vessels themselves. The site went into supply just at the end of April, and we had detections within July. We didn't have any on the final water, but we did get those detections that was a lot earlier than we expected. We had to replace the GAC media, and one of the other things that we encountered that we didn't account for within our design parameter was that one of the key PFAS compounds, PFBA, was higher on the post-GAC level than the raw water. So there was a suggestion that there may be some desorption of that because the GAC had a greater affinity for other PFAS compounds. And those two types of PFAS compounds that I'm talking about are the short chain molecules that are a lot harder to remove by GAC. So GAC is a great technology for removing those longer chain molecules, but when it comes to the shorter chain, there is a real challenge for the removal using GAC. So our expected use of the GAC plant, we was expecting at least 12 months. And we found that we were getting around 3 months. And this is because, as I mentioned, the short chain compounds PFPEA, PFBA and PFHXA showing the signs of breakthrough. And going back to what I said earlier in terms of the efficacy of the treatment process, it really is dependent on what you've got in your raw water, because having those present created a challenge that we was not expecting to have it as a shorter version. And just to say about the operational costs, we're talking about £150,000 every time we need to replace those GAC vessels. So it is a big operational cost that wasn't accounted for when we think that we could go 12 months from that. So where are we now with source to nil? Final water breakthrough occurs on our short chain compounds. When the total PFAS exceeds our internal limit, the site is removed from supply and we have to replace the GAC, which is happening roughly every 3 months. The GAC pilot plant is absolutely key for predicting breakthrough. And as I said earlier, the sampling frequency and lab turnarounds have to limit how conservative you need to be on the trigger levels, because you cannot, as I said, if it was a 24-hour turnaround time, we would be able to be a lot more lenient, but we cannot risk or have water that's going above those guidance values to our customers. Carbon change logistics and the disposal route can be problematic, especially, as I said here, when we've got early exhaustion, and the lack of backwashing has been highlighted as an issue, but it comes with other challenges by retrofitting that into the process. So we are continuing to look at an assessment of options for the future operation of the site to determine the most effective way to operate the plant. So is it a long-term solution? And is there another technology that is becoming preferable? Well, I would say in terms of the 3 months compared to our 12 months, the media replacement frequency for cost and a carbon point of view is problematic, especially with disposable costs, embedded carbon, the extra haulage, etc. For ESG, it is not great practice for us, especially when we're looking at net zero strategy and resilience planning. The whole life cost really does need to be taken into account in that versus capital cost. We don't have the answer yet. We are still ongoing with this, and we are looking at other technologies on what we can do, which I think will feed nicely into hearing from David and Kathy now into our next presentation. Thank you.
Thank you very much. And thank you to Barry and Dean and the whole Pipe Guild for hosting us here today. So I am going to go ahead and share my screen. Let's see. All right. All right. Can you see it?
We can.
Excellent. Okay. All right. I'm Kathy Swanson. David Hayhurst is also with me.
Hello.
Okay, excellent. So I live in California. I've been doing ion exchange for almost 20 years, especially groundwater contamination cleanup. Started with perchlorate a long time ago. Of course, it's morphed to PFAS. David, do you want to give a brief introduction?
Yeah. Hi, I'm Dave Hayhurst. I look after the UK office for Ecolab Purelight. I've been in the ion exchange business for quite a long time now, and so I'm the general point of contact for any UK-based questions on any ion exchange issues that anyone may have. Kathy, hand over.
I live in Orange County, California, very close to Disneyland. And I was getting ready to do a talk about a year ago, and I got this brochure in my email from my local water district. So Orange County Water District has treated 53 billion gallons of water, and that's converted to cubic meters over 200 billion. And all of that has been treated with ion exchange. And I thought, wow, that's really cool, because I think 80% of all sites treating PFAS in California are treating with ion exchange. And so I sat down and I tried to estimate how much of our water in the US is treated with ion exchange when looking at PFAS. And I estimated over 85,000 cubic meters per hour are treated with single-use resin in 2024. And that's probably grown in 2025, and I should probably update the slide, but it's still a pretty big number. And why is that? Why has the US embraced single-use ion exchange technology? Now, I want to clarify, when I say single-use, it means that you use it and dispose of it. So there is no waste stream with a single use. So a couple of reasons. Fast kinetics means smaller footprint, which means lower capital cost. High selectivity is longer bed life, which means lower operating cost. And then because you're using less media for longer periods of time, you have less waste generation, which leads to better sustainability and lower operating cost. So what I hope David and I are going to show you today is a little bit of data to substantiate everything I've got on this slide.
So in the UK, how prevalent is ion exchange? Well, it's actually used extensively in the municipal space, specifically for nitrate removal, and also there's a installed plant removing chromate at a municipal scale. Outside of municipal water, it's a standard technology used in all nuclear applications. It's in all breweries. It's in pharmaceutical applications. Anywhere where you've got a process stream that needs treatment, then with an ionic constituent that you want to remove, then ion exchange will be present. Every sugar cube that you produce, that you eat, has been run through an ion exchange resin to decolorize, for example. So it's a very established technology, decades and decades old, and where we understand the technology extremely well. So today we're going to talk a little bit about PFAS applications. So we're going to cover what is PFAS in some reasonably high level detail. We're going to go to the regulatory stuff both in the US, Europe and the UK. We'll do some ion exchange, not too heavy on the chemistry, but a bit of an introduction. Then we'll get into some system design, and we'll finish up with a case study of an example of a plant design and install in the US.
So this was covered, so I don't want to go too deep into it. Just know that there are thousands of species and many, many sources. We're not looking at treating all of them at this point, but why do we care? It's because it's bioaccumulative, environmentally persistent, and linked to a variety of healthcare concerns. Barry did a very nice job in the beginning, so we are going to skip over that. In the United States, this is a map from the Environmental Working Group that looks at where PFAS detections have been found. So there are some states that are treating more aggressively than others. We do have different regulations at the state level. I will pass it back to Dave.
Yeah, so following on from the US example, and how significant is the issue in Europe and the UK? Well, Le Monde actually put together a data set some time ago, collecting every published PFAS figure in Europe, and this is an interactive map. So there's the European map and the UK map, and it records known contamination and known users and some presumed contamination. And you can drill in, and if anyone is so inclined, you can drill in. This is in fact based on where my house is, so I now can have the joys of looking at all the PFAS contamination in my local area. And so this is all readily available information for people to be able to see the extent of the issue. As you can see, it's fairly significant. So into some regulatory stuff.
So this is what the current regulatory levels are in the United States. There are some questions as to whether the HXS, PFNA, the GenX, and the PFBS are going to continue to be regulated. But as of right now, this is the current guidance for compliance in 2029. One thing you'll notice is they do not contain as many short chains as you do over here.
Yes, so despite the existence of all sorts of harmonized regulations across Europe, obviously every European country has gone their own way. So Denmark has gone extremely tight with their regulations, Sweden following suit, and Germany is running on the EU standard, which we'll go into in the next couple of slides. UK, as Cara mentioned, currently setting a limit of 100 ppt across initially 47 and now 48 specified compounds. And we can break down that European 20 into a bit more visual list. And what we can see here is the sum of PFAS. So these 20 occur on all the UK lists as well. And we just add some extras as well to get up to our 48, just because we do. So in terms of these, you can actually group these molecules into two different types, as illustrated here. So depending on the functionality of the molecule and the chain length of the molecule affects how the molecule will load onto your media that you're using to remove, as Cara alluded to earlier. So anything with a sulfonic acid group on will load nicely onto an ion exchange resin and stay fairly firmly bound. Anything with a long chain, so anything above C8, octanoic acid, PFOA, will load quite strongly. Anything with a carboxyl group and with a shorter chain, so the butyl, pentyl, hexyl and heptyl species are more challenging. Now, so I think we just probably talked about this already. So the way the system works in the UK is 10 ppt is considered tier 1. If you're working between 10 ppt and 100 ppt, that's tier 2, and that's a monitor. And if you're above 100 ppt, that's so you've got to do something about it. And if you've got to do something about it, then you need to bring it back to tier 1. So if you're above 100 ppt, you should be expected to be targeting 10 ppt and below in your treated stream. And this is managed through the usual DWI regulation of Regulation 31, for those who are unfamiliar with it. And this is the controlling regulation for all materials that are going into municipal water supply. And that includes things like ion exchange resins. So we have ion exchange resins that are already approved for municipal supply for PFAS, and we have a number of resins going through for nitrate, and we have a number of resins that are going through for PFAS remediation at the moment, with pilot testing ongoing. The way these things tend to work is that the approval process is fairly lengthy, so the recommended approach is to be trialling in parallel with your approval process, so that you have your trial data ready for when the approval process is complete. These materials are used widely across Europe and the rest of the world in municipal applications, and we've been producing them for many decades, so we're very confident that there won't be any issues with approval. So the route forward is parallel testing and approval.
So let's go over some single-use ion exchange basics. And the reason I'm starting with single-use is if we go back to that chart that David was talking about, this one, what you see is the majority of the compounds that we're looking at are suitably removed with single-use resin. And those are the same compounds that these single-use resins are targeting in the United States. So I want to go over a little bit of how they work, and it'll help you understand the background for it. So as mentioned, these are carbon chains protected by fluorides. Fluorides are kind of like the force fields, right, that protect that bond and keep that molecule healthy in the face of sun, heat, oil, things like that. It's the sulfonic head, the ionic head, that allows the molecule to be water soluble. Till they figured out to put the ionic head on it, they couldn't even use the fluorocarbons. And so that's what this does. So we take advantage of this ionic head, and we capture PFAS through ion exchange. That ion exchange is a very fast and very strong reaction. And those fast kinetics allow us to treat very quickly. So the typical contact time for GAC is about 10 minutes. The typical contact time for ion exchange is 2 minutes. So you can treat 5 times more flow through this through the same footprint. There's a secondary mechanism as well for absorption with ion exchange beads, and that is the ion exchange beads are actually like a plastic polymer. So you get this this entanglement of the PFAS molecules into the bead. And the reason we know that is because the PFAS actually loads beyond the theoretical capacity of the ion exchange bead, meaning it holds on to more PFAS than the number of active sites that we have, and that's due to that entanglement. It also means that it's very difficult to regenerate a single-use resin. The reason is because of that entanglement. And so there's a couple ways that we look at regenerable resin. One is a solvent regen. Now, a solvent regen would swell the bead. You use a solvent and a brine. Now, that has been done on military installations and with industrial sites, but obviously using a solvent is not appropriate for a drinking water application. So that is really not done at this time. So from a single use, I mentioned the very fast kinetics. So essentially, here's your ion exchange bead. I like to visualize it as this magnet, but of course it's an ionic thing. So you're literally exchanging a chloride for your PFAS here. And how does it know to exchange the chloride for the PFAS? It has to do with selectivity. So nitrate, sulfate, chloride, alkalinity are all in the water, but it is more selective for anything as you go up the graph here. Remember though, that these ions are in the water 1,000,000 times higher, ppm versus part per trillion. So while it's more selective for PFAS, there's also the concept of competition, and it's the background ions that really drive the throughput for ion exchange resin. Here's a little data to kind of substantiate what we just said, and you can see the order of breakthrough. And that x-axis was in bed volumes. And bed volumes is literally just the volume of media in the vessel. So it's the bed depth times the area gives you your bed volume. And you can have the x-axis in bed volumes, you can have it in days, or you could have it in money. I think everybody speaks wallet, and that's really what it comes down to, is what does it cost and what are your triggers? So yes, go ahead.
Outside of the US, as we mentioned, the focus has been quite significantly on short chain as well as the long chain molecules. So there's work is ongoing to look at tackling these short chain molecules and how we can manage those. And the route we see mainly pursuing here is looking at regenerable solutions. So if we click to my helpful graph, there we go. So as we've alluded to previously, if we look at the effects of chain length on the capacity in terms of bed volumes, as Kathy's introduced the concept of bed volumes, we can clearly see that as the chain gets shorter, it's much more difficult to securely load onto the bed. So this lends itself to a regenerable solution. So in the single-use systems, as I say, we can use a solvent system, but they're not really suitable for municipal supply. But in the case of dealing with regenerable systems, we can switch over to a different type of resin, which is regenerably. And if we switch to the next slide, we can go into some details on that one. So the selective wheat-based resins, we can run slightly acidically, and by using a bit of caustic, you can then regenerate the short chain molecules from the bed, and then you have a PFAS laden waste stream which you can then run through a destruct technology. So where we see this one, practically speaking, is that the longest term solution for dealing with PFAS will probably be a combined approach with a single-use media to deal with the long chains, and then a regenerable media to deal with the short chains. And we've actually looked at this specifically at modelling at the Sawston facility, where we think that based on the data we've got so far, we probably bring down that change out point. We've increased from 3 months to probably about 8 months using a single-use combined with regenerable system, and reduce the volume of resin or disposal material down from 20 cubes down to about 6 cubes every 8 months. So we can see that immediately by using this combined approach, we can, and tackling the short chain molecules via a regenerable system, that gives us a significant improvement in terms of waste stream.
So when we talk about waste management, that's usually one of the questions I get. So right now with ion exchange resin, you can landfill, you can incinerate. With GAC, you can incinerate or you can reactivate. So those are currently commercial. Supercritical water oxidation is also a promising technology. And those are basically the treatments for solid waste. Most of these other treatments are good for liquid destruction. And that's also where regenerable resin is ideal, because for the most part, these need to be looking at a liquid stream for destruction. So let's get into system design a little bit. So the first thing that we're going to start with is water quality. David will email you a chart that looks similar to this in Excel. It's extremely important to know the background ions in order to accurately predict how long the PFAS is going to last. Other things that are extremely important are things that can foul the resin: iron and manganese, suspended solids, oil and grease. We need to know those up front to know if any pre-treatment is needed. So in the United States, I am one of the co-chairs of the American Water Works Association committee for ion exchange, and the subcommittee that is writing a standard for ion exchange resin. So this standard is called B104-24. And we were writing one guide for all types of resin, single use and regenerable. But when the MCL came out for PFAS, we pivoted and said, look, we really need to get the single use guide out as soon as possible. So this is available. You can find it on AWWA's website. But because I wrote that, I've also written some internal guides, and these are essentially the parameters for design that you're looking for. And we've got a whole guide. You can go to our website, you can scan this code, and these are guides for drinking water and one for environmental discharge. So what we really want to do is present this case history from Los Angeles, just a few miles from my house. So this was Pico Water. And what we did, we started with a water chemistry. A couple things you'll notice, they do have fairly high sulfates, 120 ppm, which does, it's one of the competitors for throughput, but still very, very good throughput here. So this is our model, a total of 54 part per trillion of total PFAS. Of all of these compounds, PFOA is the regulated compound that drives throughput, even though PFOS is much higher than the PFOA, which is 12, the PFOA breaks through faster. So the other thing that is important to look at is where is your endpoint, right? And so here we're looking at what the lead bed is going to do, the virgin lead bed, the repeatable lead bed, and the lag bed. So all kinds of ways to look at it, and that's something that we can also model. So we modeled it. They also did an RSSCT, a rapid small scale column test for GAC, and got about 27,000 bed volumes. Our modeling showed about 270,000 bed volumes. So we decided that we needed to validate it. And so what we did was an accelerated pilot. And what you can see is if this was a full bed depth and they're segmented columns, we have 25, 50, 75, and 100% sample ports. And so we can watch the PFAS mass transfer zone through the bed and get results at the 25% port, which reduces the amount of time that we need to pilot. So this accelerated piloting, you can see you get breakthrough a little faster, but it is more conservative, right? So the 2-minute empty bed contact time is going to last a lot longer. The other thing is, and we've worked with the regulators on this, if we can accurately predict ion exchange under unideal conditions, then you can also trust our model under ideal conditions. And we've done quite a number of accelerated pilots throughout the United States. So this is the same graph, but instead of bed volumes, it's in days. And this makes the obvious point that you get results much faster, within weeks instead of months to years, piloting, full bed depth. So here are the results. So this was our model. Here's our actual, and so you can see our model was conservative yet accurate. And when we plug this into our design formulation, we get 4 vessels. So this was a 681 meter cube per hour site. So we're using 2 3,500 millimeter vessels. We call those 12 footers. On the ion exchange, on the carbon side, they were using what we call 40,000 pounders. And so these vessels are still 12-foot diameter, but they're much taller so that you can fit more carbon in there. And this is the site. And a lot like a lot of sites in Europe and the UK, these are older sites. They don't have a lot of room. They didn't plan to treat PFAS when they drilled this well. This is the site and the constraints. We've got a liquor store on one side. So quite a lot of, building and stuff around, not much room for expansion either. So this is what the ion exchange system would look like. This is what using 20,000 pounders would look like. And for the 40,000 pounders, they would only need 4 vessels. So much less equipment with ion exchange. The other thing you notice is that we've got 10 times the throughput with ion exchange. This is very typical. Typically, ion exchange is going to get anywhere from 5 to 20 times more throughput than GAC. And it's interesting because 5x is kind of that break-even point where the cost of ion exchange versus GAC and all the disposal and everything, that's your break-even point in terms of when ion exchange is going to be more economical. So we got 10 times the throughput here with the GAC. The other thing to notice is in terms of media consumed per year. It's consuming 10 times more media, which means 10 times more waste that we have to deal with. I did not convert this one to metric, but at the end of the day, what you see is because you're using less media with ion exchange and it's lasting so much longer that the operating cost was half for ion exchange than it was for GAC. Now, these numbers are based on 2023 data, and it includes media, installation, and disposal. So it is a turnkey cost baked into those numbers. And this is the happy ending of the story. So they did go with the ion exchange. It was filled only a few months ago, and it has been treating PFAS very successfully. So a couple of other brief things before we finish. You know, in terms of sustainability, when you have a media that's lasting 5 to 20 times longer, you know, you have that many less replacements and reactivations. So from a sustainability standpoint, you have a lot less trucks on the road. The other thing is when you reactivate, it's going to a kiln that runs at very high temperatures and then goes to an afterburner. None of that energy is reclaimed. Ion exchange, for the most part, is going to an incineration facility. Those incineration facilities are waste to energy, and they are actually capturing the BTU that are inherent in that plastic. So it will destroy both the PFAS and the resin. The wet resin has about a 12,000 BTU per pound waste capacity in it. I thought it was very interesting that Kara mentioned this, specifically with regard to PFBA. So this is a slide, it comes from the ITRC PFAS manual, but it's data that came from Calgon. And what you see here is as both PFAS, other PFAS, longer chain PFAS, and TOC load onto the GAC, the concept of chromatographic peaking is going on here. So it's actually sloughing or rolling over the PFBA at almost twice its influent concentration. So you take enough data points, you will see this for PFBA. Now that's going to happen for every short chain at just different times. And you can already see the PFHXA is starting to come up. It will also peak and then go back to its influent level. So that's one thing to know about carbon. Carbon can also do the same thing with nitrate. If you have a well that doesn't run 100% of the time, what will happen is as it sits in the sun, the equilibrium constants will change, and you start, when you turn the well back on, you will start to slough nitrate off of the carbon. That does not happen with ion exchange. So one of the sites that I worked on in Colorado went through this testing with ion exchange because they had experienced it with carbon, and it was very clear that ion exchange did not slough like this. So waste generation, we talked a little bit about the amount of waste generated. So this is based on cubic feet of media on site and cubic feet of media consumed per year. When we look at destruction, Calgon has done a study with the US EPA showing 3 and 4 log reduction of PFAS. And Clean Harbors has done a study with the EPA showing 6 log reduction of PFAS. So incineration, people always ask me, well, does it actually destroy it? And the answer is yes, it does. So carbon and ion exchange can be used together. Generally, GAC precedes IX, but you can do it either way. Now, if you do have GAC in the front and it's sloughing the PFBA, just know that your ion exchange will see that as well. The other thing to note is that if you are treating anything else in that water with an anion resin, like nitrate, that nitrate resin has been loading PFAS for many years, has probably loaded it and broken through. So we had a site in California, City of Rubidoux, and they put GAC treatment in front of a nitrate treatment system. When they put that GAC treatment in place, this resin was already loaded, and they started to get a slow elution curve with PFAS coming out. Even though it was 0 coming in, there was PFAS coming out because the equilibrium force had changed. So what we ended up doing is an emergency replacement of 1,500 cubic feet of ion exchange resin in order to get them into compliance as quickly as possible. So just something to keep in mind as you're designing these plants. I know there are a lot of nitrate plants throughout the UK. So hopefully we've given a case study, we've given some data that shows you that between the kinetics, the selectivity, and you know, the less media and longer periods, that from a cost and efficiency perspective, that it's extremely beneficial and sustainable. You know, as we get into some of the shorter chains, we did not dive into the regeneration of short chains, but it's definitely an option and something that would be used in combination with either a single-use ion exchange or a GAC. And with that, I think we've got a couple minutes for questions.
Thank you, Kathy, David. That was really interesting. I did run a little bit over probably the time that we were going to put in, but it was extremely helpful. At this point, Dean, I wonder if you could share just a couple of words from the supply chain, and we'll come back to questions if we could.
Absolutely. I'll keep it short and sweet. Hi, everyone. Thanks, Kathy, David and Cara. So my name's Dean Adams. I'm Head of Account Management across On-Site, IWS, M&E and G-Stoke PLC, part of the South Staffordshire Group. So we are effectively the supply chain, the end user, the contractor that will go in and install this plant. So we work very closely with our water company clients to make sure the solutions that we deliver actually meet the operational needs on the ground. So across the three businesses, we are starting to see PFAS has been a major issue within the industry. Ion exchange isn't yet the universal long-term solution, but it's clearly the direction of travel, just based on the TOTEX costs, really. So operational costs and maintainability of GAC becomes an issue, and the smaller footprint and longer bed life as well. So, but that being said, GAC definitely still has a place right now. It's quick to deploy, and the water companies and our clients, which we work with the majority of the UK water clients, are familiar with it. So they know how it operates, that it's tried and tested. It's a little bit boring, but it works, but it can be expensive. So as Cara highlighted in her presentation, there was a project completed at Sawston Mill, which IWS M&E installed. There's some Chenviron GAC filters, but we experienced breakthrough much quicker than anticipated due to the water quality. Following that, we ended up installing a pilot plant to try and help trend the sort of breakthrough curve because of the lack of live monitoring on the PFAS, to try and trend that sort of 25% quicker. So I suppose what I'm sort of saying in summary is that both methods currently have their benefits. GAC is quick to deploy, but ion exchange certainly has the longer term benefits in terms of that sort of TOTEX solution. So it really depends on what drives the water company's requirements, I suppose. So that's it from myself. You know, I wanted to keep it nice and short and sweet because I am conscious of time, but essentially we will install what our clients ask us to, but we will give our advice from a TOTEX point of view and what's the most energy efficient. Thanks, Barry.
Thank you, Dean. I think that is quite important to note, and from a supply chain perspective. So just rounding up a couple of the questions. I know we are, as Dean says, short on time, but some of them are quite important. Cara's teed up to answer Lauren's question. Thank you, Lauren, for putting that in, around the measurement of the PFAS.
Yeah, thank you, Barry. So I did just quickly type out something there, but probably easier to say it. But yes, we do outsource our laboratory techniques. We don't have that in-house. Some companies do. But it's the turnaround time, mainly because of the levels that we're looking at. Like, we're looking at nanograms per litre, which is such a small concentration. It also has a number of complex preparation techniques, and also you can't have anything that can have background levels of PFAS because we're measuring at such low concentration. So there's a whole aspect that needs to be prepped for that. and because of that, because of the preparation, because of that, you have to make sure there's no trace contaminants. They like to batch up samples as well, so you might be waiting for other samples to come in. There isn't any on-site measurements as such. I think that would help everybody is if we had a PFAS monitor. I don't know if how quickly that would be around, but yeah, it would definitely speed things up, Lauren, but unfortunately not in the market at the moment.
Thank you, Cara. Thank you, Lauren. Lauren's also put a question in. If anyone else wants questions, if there's nothing there, I will definitely close us afterwards. Around destruction, and Kathy has already replied in the chat for those that have not seen it, around incineration needing to be done at the proper time as a disposal method. It's almost certain that the incineration will need to be the disposal method. I don't think we've seen anyone else do anything else worldwide when we've looked at these things. The problem with incineration with waste to energy is that we know that waste to energy plants are becoming more and more difficult to get environmental discharges, especially around nitrous oxide levels. And though they have built a few, most of those were done on previous consents and planning, and they are looking like it's going to become more difficult to build newer and more modern plants across the UK. There are a competing push from BEIS where they would like more energy to waste to manage the energy consumption and landfill issues, which I can go into in a separate webinar if everybody wants to. But the reality is that we probably need to move away from energy from waste in the long term, and the newer technologies like a biocharring pyrolysis process is likely to replace it. That will concentrate, not destroy, some of these chains in the future. So I do think the disposal route is a real challenge for all of our technologies, not just because of what we're doing today, but probably because of what we see coming down in the future. Kathy does quite rightly say that Veolia do have PFAS approved incineration currently and coming online, and I'm quite aware that some of the other large providers do too. But for now, that is a safe route, but we do need to keep an eye on what that is going to be going on into the future. So there are a few minutes over. If there are no more questions, as they've not popped in the app, I hope that everyone has enjoyed today and found it informative. Just a bit of an overview about where we are in the sector, the technologies and the great activities that have been going on everywhere else around. I would thank you for your time, and we'll close it today.